All right. All yours, Mansi.
All right, so is my screen visible?
Yes, we can see it. It's coming up. Yeah.
All right. So if my screen is visible, I'll begin. Right.
So, since you are speaking, who is my timekeeper today? I nominated somebody.
It was me.
Yes. All right. Keep the time.
Yeah.
So,
Yes.
the new entrant, Aditya, the idea is that your seniors have decided to say that we should make the presentation in 18 minutes in the format of a TED. It should not exceed 18 minutes because the attention span of a human doesn't exceed 18 minutes. So whatever they have to say in 18 minutes, followed by a question and answer session where we discuss about it in detail. Okay? All right. So welcome to the group, and I will now hand it over to Mansi so you can get started.
All right. So good afternoon, everyone. Today, in the seminar, I'm going to talk about the passive acoustics and how hydrophone data is being used to detect fish signatures underwater, which is also what I'm working on currently under my DTP. So the agenda for the meeting today is simple. I'm just going to introduce what I'm working on and basically break it down into the following parts. So first I'll try to explain what soundscapes are and what are the soundscape made of, and they're made of biophony and geophony. And post that I'll try to explain what passive underwater acoustics is and how it's actually being used currently to classify and understand the sounds produced by fish underwater. And finally, we'll talk about the current techniques which are being used and the work that I've currently taken up. Right. So to start with, what are soundscapes? So soundscapes is something like you can imagine when you're describing a landscape, you will describe, maybe the trees that are coming into the picture or a building that you see. So similar to that, a soundscape is just a description of what are the kinds of sounds which are being produced underwater and can be recorded. And these sounds don't necessarily need to lie in the human range of hearing. These could be sounds which are above and below the human range of hearing and includes sounds from different sources, right? And understanding these soundscape gives us a very it gives us an insight to understand what are the kinds of relationships that exists underwater in the natural ecosystem, as well as how this ecosystem interacts with the external ecosystem or the man-made ecosystem that occurs on top of water. So, right. So now when we're talking about soundscapes and the sounds that are produced within the soundscape, it's made up of two kinds of sources. So one kind of source is actually the biotic source, which includes sounds coming from fishes and underwater mammals. So anything living that produces sounds would be classified as a biotic source. And then there are abiotic sources of sound, which are again classified into two categories. So one would be geophony. So these would be sounds which are produced either on the surface of water due to rain, wind, and waves, or it could be sounds that are produced underwater due to the activities on the seafloor, like earthquakes and volcanic eruptions underwater. And another category of sounds that we also observe underwater would be the sounds that are produced due to human activities. And they are mainly due to shipping activities, but they could also include sounds from drilling and other activities which are happening in the nearby area. So after we've spoken about what are the different sources of these sounds, it's important to understand why are we even interested in understanding these sources and studying these relationships. So because fishes in general, they navigate and communicate with each other using the sounds that they produce. It's a very delicate balance that occurs in the underwater ecosystem, and because of human activities, it's actually something that's getting disrupted, especially around the harbor areas where the shipping traffic is higher, areas where there are a lot of drilling and mining activities. So it becomes very important to study these soundscapes to understand what's the effect that humans have on this environment, as well as just study the water environment to gain more knowledge about how those ecosystems work usually. Right. So coming to the main topic here, that what is passive underwater acoustics. So when we're talking about the oceans and how we can actually look at the oceans, it could be in different ways, right? So you can do visual surveys where you look at the ocean and see how the ocean is behaving or how the species near shallow waters are behaving. And there could also be other ways to survey the ocean, like trawl surveys, which use sonar technology to study the underwater to study underwater. But bottlenecks of both these techniques are that with respect to visual observations, after about 100 meter or so underwater, there is no light which travels through. So you cannot really have visual surveys occurring after that. And with respect to tall surveys which are done using sonar technology, it's usually done through ships which again disturb the underwater environment. So you cannot really capture the true nature of these biotic sources, at least in case you're using trawl surveys to study this environment. And here's where passive acoustics comes into play. So passive acoustics is like a non-invasive technique. So basically what passive acoustics would mean that we are sitting underwater and we're not participating in the environment at all. We're just sitting underwater and listening to what all is happening around us. So that is done through underwater hydrophones. And why passive acoustics is better than the other two techniques that I talked about is because one, it's environmentally safer and it doesn't really interfere with the environment at all. So it's just sitting there and listening to the sounds. And second, is very less susceptible to weather conditions. For example, with respect to visual surveys and trawl surveys, there are a lot of moving parts, and you need to take into account what kind of weather occurs above water so that you can conduct the surveys successfully. But those kind of limitations do not really exist when we're talking about passive underwater acoustics, right? And these studies, like I talked about, they actually are conducted using hydrophones which are deployed underwater, and they could be either moved to the seafloor or they could be deployed using a stationary station over water. But these are very useful because at per deployment they generate vast amounts of data. And to give you a sense of what kind of magnitude of data they produce, so per deployments they produce hundreds of GBs of data, and that's very useful for people who want to study the underwater environment. And they offer again minimal interference with the ecosystem, and we can capture the true nature of the underwater ecosystem. Now, the main focus of our study is, of course, like studying biophony and see how we can classify different underwater sources. So the major focus of segmentation would be on biophony, and we also want to figure out what are the other sources which are also occurring. So with respect to biophony, it's pretty interesting to understand how these sounds are produced and how they are classified. So I'd like to break it down into three parts. So one, why do fishes produce sound, right? So they produce sound because that's the only way they can actually communicate underwater, and that's what they use to navigate through water when they're trying to find habitats for feeding, or places where they can actually mate with each other and reproduce, right? So for them, sounds are a very important means to communicate and navigate. And with respect to the activities in fishes which would generate sounds, so these are either through clicks that they produced using their bladders, or it is because of the fish, if it is because of the fins that they rub against each other. And some of the fishes, like you must know, that whales actually use echo calling, which could be to a, heard across large distances. So those are the different ways in which fishes would produce sound. And the interesting fact about this is every fish species would have a very specific kind of sound they produce, and a very specific way, which is very specific way to produce sound, which is something that we can determine by their biological behavior. So that is one way in which we can actually classify fish behavior. And while we are recording all of these sounds, the specific things that we are looking at for classification would be the duration of the sounds that are produced by these fish species, and the pulse repetition. So how often do these sounds occur in when they're occurring in a streak, and then the peak frequency that these fish shoals would reach, and also the frequency bands which occur over time. So these would be a few characteristics that are currently being employed to study these fish characteristics. And to give you an example, these are the different kinds of fishes. This is just an example of different kinds of fishes, and how the sounds they produce look very different if you see them in a frequency and time domain. So these are the different ways you can see, like the pulse repetition is changing, the duration of sound that that they are producing sound for is changing, as well as the frequency or the peak frequency is also changing across these species. Right, and this is another example that we've taken up from a study which was conducted by NIOT. So you can see that there are two examples here. So one is, let's call these two as species one and species two, and you can see how their sound characteristics are very different from each other. And a number of these sound characteristics are currently used to classify these species if we know what kind of species we are looking for. Right. So most of the classification that has been done till now is based on supervised classification techniques, and it also makes sense because you also need to understand, if you want to classify which species this particular sound is belonging to the very species, right? You need to understand what is the biological behavior of these fishes, or what is the maximum frequency range that they'll produce sound for, right? So that's why supervised classification techniques are more popular in classifying these fish species. And today, as we are speaking now, there are vast amounts of data available, underwater data available, because of the hydrophones that we're talking about. So there's publicly available data which is terabytes in magnitude. But the only bottleneck here is that when you're trying to classify fish species using supervised classification, somebody needs to manually tag these fish sounds, and that is usually done by operators who look at the spectrograms of these different fish species and tag them as different species potentially, and then these tagged fish data or labeled fish data is then used to train our algorithms to classify fishes from different sounds. And to speak about some classification techniques which are currently being employed. So one way is to look at label data. So this would be in forms of spectrograms. And this is the data that you're going to get through underwater recordings, and then compare it with data which we already know belongs to a certain species. So this would be either by matched filtering or by spectrogram correlation. So to give you an example, it's like a fingerprint of fishes, like me and Sir discussed. So if you compare different spectrograms, you can actually match spectrograms to see if the sounds is actually coming from a particular species. And the second way to do supervised classification is by extracting features and detecting the sound durations of these fish calls, where we can detect what is the absolute change in the frequency. So I showed you some graphs, so you could have seen that the frequency ranges changes over time. So what's the absolute change? And we can extract these frequency features and then run supervised algorithms to figure out what kind of species does the sound belong to. Right. And in my DTP, what we are trying to work on is to build an automated detection and classification system, which we'll call automated DCS. So the intention with this detection and classification system is that we have a lot of unlabeled data available for us publicly. So we want to be able to take that data and run our classifier on that and automatically detect at least how many sound sources are present in this audio data that we're talking about, and potentially look into if we can also classify fishes based on based on these clusters that we have made. But the only difficulty in producing these DCS would be first to if we have to figure out a way to generalize these classifications across different species. So till now, whatever studies have been conducted, they are very localized. So for example, on specific species or around specific geographies, and hence it's difficult to generalize such models overall across to study global audio data. Second, there's a lot of noise produced when you're trying to record underwater sounds, and there's a low signal to noise ratio. So that's again a bottleneck when we're trying to pre-process the data to figure out which signal is of interest. Then third, again, as I said, there's a difficulty in obtaining labeled data set and figuring out what kind of sounds are actually produced by fishes and which kinds of sounds are produced by abiotic resources. And finally, the last bottleneck here is that some fishes are very small in number, and their vocalizations also occur in very low frequency ranges. So that results in unbalanced data set, which could lead to our classifiers classifying these fishes in a wrong manner. So these are some of the bottlenecks which have been identified so far with respect to unsupervised learning techniques in this audio classification arena. And with respect to my current direction, what we are working on right now is we have identified a source of audios that we want to use. So it contains audio data recorded in the Atlantic. So we are trying to pre-process the data to extract the frequency feature, and then we are planning to use clustering techniques to classify different sound sources together. And we're trying to potentially use the Gaussian mixture models here to be able to classify sounds based on the probability of them belonging to a certain species. So this is the current direction, and that's what we're working on. And I'm open to questions now.
Okay, all right. So, questions?
I had the question about the low signal to noise ratio. Like, what is the way to tackle that?
Right. So I think that's what I also am working on. So one way to tackle that is again like so there are two things that I've read about till now. So one is you actually still perform classification with that noise, and if your classifier is able to detect that this noise is consistently coming, it will classify that again as a separate source itself. So that's one way. And another way to tackle this is to actually pre-process data before you're using that. So that's an area I'm still exploring. But the way you can do that is only take, like if you figured out what kind of fish species would probably be occurring in the area that you're talking about, you can only take particular frequency ranges and filter sound according to that. So say for example, even if data is recording till 256 kilohertz of sampling rate, you can just reduce it to 8 kilohertz and only consider sounds in that frequency range. So that if you know that noise is coming from a particular source and its range is different, you can try to pre-process the data out.
No, wait a minute. Sampling frequency is not the same as the cutoff frequency, right?
Yes, sir. Yes, sir. So sampling frequency would be different. So if you know that your fish sounds would be in a particular frequency, you can only filter those frequencies out and listen to that data. So that's one way of pre-processing it, and then in that sound you can try to see if you can either cluster the data out, cluster the noise out, or if there's some way to figure out what is the frequency range of the noise produced, because that is something that doesn't change as much in the audio data. So you can try to just filter that out as well.
Yeah. So what approach will possibly you be trying out first?
Right, sir. So I think I'll go for a pre-processing approach because that is something that a lot of all the classified techniques are also using. So I try using that, but I'm still working on
No,
that.
I think the way I think about this is you generally you can either do a what you call band pass filter
Mhm.
or a low pass filter, right? If you are doing a low pass filter, you are cutting off everything which is in the high frequency regime, where you don't expect to see much of the sounds coming from the sources that you are interested in classifying, right? So you only use the low frequency sounds and then you try to work with that data. Or if you are looking at a band pass filter, you can select a band of frequencies within which you want to keep the signal. Beyond those two frequencies, cut in and cut off, you are removing everything out of it using a filter, and then you are saying that now I'm going to purely look at the signal from a perspective of whatever is happening in this band, and I classify it into different clusters. Right?
Right.
Okay, all right. Any other queries, thoughts, comments, suggestions?
I have sir, one. Why you are specifically targeting to Atlantic Ocean? Because you have told that you are basically trying for Atlantic Ocean species. So why there is a specific means? Do we have any large number of data available in that region, and that is the reason, or something else?
Right. So the initial scope was to actually take data from some other source, but since that data is not currently available to us, we try to figure out if there's publicly available data which we can use to maybe just make out an approach to classify these
But it is
filters.
available now, right, Mansi?
Right. So I was talking about the NIOT data which is not available, but this data which we are talking about, the data which is recorded from the Atlantic Ocean, it is a file which is publicly available on AWS. So I don't even need to download that data. I can directly use it from the AWS bucket. And the
Correct.
good part about it is like it contains vast amount of data across different parts of the year.
You're
So you
looking
can.
at which data set? Is it the NOAA data set or the
So it's
Mars?
the MBARI data set.
Yeah, Ambari is not in Atlantic. It's in Pacific.
All right, so I think it's still in the Atlantic, but I'll check upon that.
Ambari is located on the west coast of US. It's the Pacific Ocean. Monterey Bay is also in the Pacific Ocean. The hydrophone is located there, right? Because it is a
Right.
Pacific Ocean data set, and that bay is very famous. They have a big aquarium there, which houses many different species of mammals and marine mammals and other things. It's a very exciting place to be. And they generally go out into the bay and collect data about a lot of mammals. especially the whales. They travel from the Alaska region to the California region, and they cross over from the Monterey Bay. So they are able to catch a lot of sounds from the bays for the whales. And there is a big whale watching tour which goes on during the season, where you can watch even the blue whale, gray whales are regular, and then humpback whales. So you can see all four species of whales generally in that place. So it will have probably sounds of many different species, right?
Yes, sir.
So what you can do is you can look at some of the work which Ambari has published and see as to what is the range of frequencies in which these are falling. What is
Yes,
the
sir.
minimum and what is the maximum over all the mammals? And that can be a bandpass region, a good way to think about that, right?
Yes, sir. So in the Ambari dataset, I think they've divided it to three parts. So one is 8 kilohertz dataset, and there's a 16 one, and then there's a 256 kilohertz dataset. And because they know that some whale species would produce sounds or produce low calls or high calls in those frequencies, they are studying those particular
No,
datasets.
I don't. I think you're getting confused. That is not frequency. That is sampling rate, right?
All right, sir.
You don't need 256 kilohertz sampling rate because you are sampling at very high frequencies. You know that there will be nothing in there, so you can go with the least one. But
Right,
even in the 8 kilohertz data set, you don't need to consider everything from 0 to 8 kilohertz. You may have a cut-in frequency at maybe 2 kilohertz to 8 kilohertz, depending on what is the lowest sound which the mammals produce. So that can help reduce your frequency content and can reduce your feature vector. Right?
all right.
All right. Any other queries?
Hello.
Yes, Aditya.
Yeah, Aradhya, you want to go first?
I can. I have no issues.
Okay, go
Okay.
ahead.
Tell me one thing. Once you are done with this thing, and if I give you a sample, like if I give you a sound sample,
Mm-hmm.
what will exactly happen to that once we feed it into your model?
Right. So, see, the current direction is that we want to, like, if you give me a sound sample, we should be able to classify that at the very least as something which is produced from a biotic source or an abiotic source, because those are two distinct things that we can classify. And within the
Hello.
biotic source, also, we want to be able to classify it into not which species it belongs to, but at least in a cluster of
Uh,
species which we can look at
Hello.
differently. Hello. Am I not audible?
Is my internet bad?
Both of you are audible.
Yeah, I can hear Aradhi. I think he can't hear me.
Wait. I'll switch my internet. Yeah. Am I audible now?
You were
Yeah, you are.
audible throughout.
Yeah. Sorry. So you were saying you will feed the sample to your model and something. Then I missed.
Yeah. So we should be able to, like, the main idea here is that whatever kind of model, whatever kind of sound it is, we should be able to at least classify it to a source. So the major buckets of those two sources would be biotic and abiotic. And within biotic, we also want to be able to see that if your source contains sounds from multiple species, and if they lie in different kinds of sound frequencies, we should be able to classify them as different classes. Even if you're not able to tell which species that belongs to, we should be able to classify them as different classes of fishes.
But won't it happen in the case since sounds travel in the form of waves, it might superimpose and change the way we look at it. So won't that cause an issue?
Right. So if I'm understanding your question correctly, so if the sound is coming from a very distant source and like its characteristics are changing, it would
Yeah.
lead to misclassification. Is that your question?
Yes. Yes.
Right. So
And also that sound will interfere from the local sound that you have. Like it
mhm.
might superimpose with it and may produce different kind of sound waves, and also won't that be a problem? And like
Right. So I think that's an interesting question. But I think the way it's done is, again, one, uh, I think it depends on the range on which your microphone is also actually recording sounds. But I think the characteristics of at least the low frequency waves or the low frequency sound waves wouldn't change over distance. but the ones for the high frequency one might change. So I think it's definitely an interesting perspective which I have to figure out how they're actually classifying that as of now. But yeah, I'm not too
I
sure.
actually doubt that the frequencies might change considerably. They may get dissipated, but I doubt that you may see a dispersion happen. So it may diffuse, but may not disperse. Unlikely, I think. Okay, so unlike the what you call ocean waves, which are dispersive in nature, which means as the wavelength changes, the speed changes, right? But I don't think the frequency of the sound wave itself will change by a significant amount, to my knowledge. But you can correct me if I'm wrong on that. My understanding would be that even if you had multiple sources, okay, as long as they are in the same frequency zone, then is where the problem will lie. But if they are in different frequencies, if you have a high frequency ambient noise and a low frequency whale sound, when you take a spectrogram of it, you will clearly see two different bands. The frequency range in which the whale will be there will be different from the frequency range in which the noise is there, right? And as you are going to be classifying, I think you didn't kind of talk about that. So I think that is where Aradhya's question is coming about. So when you are trying to feed to the Gaussian mixture models,
Mm-hmm.
you maybe can give some idea about what is going to be a feature vector and what will the output of that model be like.
All right. So, right. So, I think with respect to feature vector, what we're trying to currently explore is just using frequencies like Sir talked about and see if we can figure out a feature vector which uses just frequency to classify these different fish species. Because I think, like I spoke about, right, every fish would have a different kind of a frequency range. So, that's one feature vector that I'm looking at, but I'll have to look at how uh, fishes who are lying in the same frequency range would differ. So probably that's where I think the duration of the sound and pulse repetition would come in. So that those would be the feature vectors which I believe would help in classification of the species, and the output would be a class. So in case when we are using GMMs, the key difference here would be that I wouldn't be calling it class 1 or class 2. I'd probably say that if we have, say for example, 3 classes, there is an X probability that the species that we have identified belongs to class A, and Y probability that it belongs to B, and Z probability that it belongs to class C. So that's what the advantage of using Gaussian mixture models is.
So it will give you a soft classification of sorts. It says that probability of this sound being from a whale is 90%, it being from a sea lion is 5%, or maybe it being from an otter is 2%, or something of that sort, isn't it?
Yes, sir.
Okay, all right. Other questions?
Yeah. So right now, your model, it takes a sound and it first classifies that into two categories: biotic and abiotic, right? So for abiotic cases, so
Mhm.
for example, they might be created by submarine or something like that. So can your model be used to classify those abiotic sources?
Right. So I think when I said it could be abiotic and biotic, I think I meant like a higher level classification. It wouldn't be like, you're classifying it first as abiotic and biotic, and then within biotic, you're classifying it as different species. But to answer your question regarding how would you classify a submarine compared to a fish. So the sounds that a submarines would produce would probably be coming from the propeller and any other moving parts inside water, right? So those frequencies again would be very different from the sound that the fishes would produce. So that's one way of looking at it. And second, even the repetition of this thing, right? So for fishes, if so yeah, I don't know if everyone would have heard of a whale call, but the whale call would start at some point and end at some point. But with respect to, say, like a propeller of a submarine, it will be a continuous motion which is happening, at least if you're recording sounds in most cases, right? So that way, even if the frequency would be in the same range, it might happen so that the repetition over time would be very different across these different sources.
Yeah, like what I wanted to say is in abiotic sources, sound will be created by, for example, submarine or
Mhm.
some any other, uh, for example, let's say a torpedo or something like that.
Yeah, maybe
So can you?
or submarines can be the
Sorry.
source. Maybe ships also, right? Ships
Yeah, yeah.
can also be a source of sound.
No. So what I wanted to ask is, can this technique be used in surveillance operation also?
So surveillance operation, by that you mean that if ships are passing by over or not?
Yeah, yeah, like something
For
like that.
example, if a submarine is passing by, can I tell is it my submarine or is it enemy submarine?
Yeah, yeah, something like that.
Right. So I think that's interesting, and that's what we'll also want to do. I think when we initially discussed about the project, that's one thing we also wanted to achieve, right? So we should be able to classify fishes and basically classify every kind of sound which is being produced under ocean. But yeah, I think once I am able to test data properly and build this whole pipeline, I'd be able to see if that's actually the case, and are we be able to identify other sources of sound as well.
I believe that it will be quite challenging and impossible to do that. Unless and until you have humongous amounts of data in your data set which is coming from submarines. Unless a US submarine is sitting there and generating sounds for you near that hydrophone, you will not possibly have much data in it
That is
in
not
order to
possible.
classify it. And it is an open source data, which means it must have been vetted very well. So the techniques are the same, and possibly the techniques may be scaled to defense applications too, but I doubt that you will see any classification which will come from your clustering. Will try to identify different types of ships or different types of submarines. You may at best be able to classify that this is something different. So in unsupervised learning, you don't know exactly what exactly you're classifying. You just create a cluster and say there is something here which is looking different than others, right? But what is not labeled. So one might have to wonder whether it is actually coming from ships or whether we are actually able to classify it from ships or not. We will not know that for sure until we hear back at the data and listen back at what is classified to see whether that was really the case or not.
So the main problem here is the data not available. So theoretically, if the data is available, then we can do it.
Correct. Ideally, that would be the scenario. And that is the major challenge also, right? If you look at it from a defense perspective too. Which enemy submarine will come and cooperate with you to give you sufficient information so that you can classify it?
Yeah, that
Nobody
is
will do that, right? So you have very minimal data to work with. So the problem there is of very little data, and I think how effective can machine learning be there is an interesting problem, is a challenging issue to look at. I mean, how minimum data do I require in order to range with the correct classification? Yeah, it's an interesting question. I would say that it's not so straightforward. Any other thoughts?
Yes, sir. One thought. And there's a Gaussian mixture model. What are this? I haven't seen this before. So can you tell me what is this Gaussian mixture models?
Right. So, okay, maybe I can like start describing maybe a K-means clustering model, and on from that I can build upon what GMMs are. So, in a K-means clustering algorithm, right, you will decide what features like are the ones which you want to cluster something on. So you have different data sets which is currently not labeled, right? And you define which features would you want to classify them on, or you can also classify them on all the features that you want to. So that depends on like your classification criteria. So if you give inputs to this k-means clustering algorithm, what it will do is look at it as, for example, right. So if you can imagine an X and Y axis, and there are different points spread across your plane, right? So what a k-means would do is it'll club nearest point. So if my k-means is say set at, for example, 3, it'll just make 3 clusters, and within those 3 clusters, all the points which are in close affinity to each other would be clubbed together. So that's very something which you do with your eyes usually, right? So when you look at a spreadsheet, and maybe I have put 3 like points across which data are spread, so you look at it and you classify that as, oh, there are 3 different kinds of data. So that's basically what k-means also does, but like on an algorithm level, that it sees what parameters match and it clusters data based on certain parameters that you define. And similarly, in what happens for Gaussian mixture models is that instead of telling you that, okay, the data definitely would belong to this cluster, it'll tell you what is the probability of this one point which lies anywhere in the plane to belong to maybe one, like cluster number 1, cluster number 2, or cluster number 3. So it's not telling you that it is for sure definitely class 1. It's going to tell you, what's the probability of it belonging to any particular classes which you have defined. Was that
Yeah.
like what
And
you understand?
one more thing. What Aradhya told that there may be some noise that may come with the fishes. So today, what our earphone does, they use the noise cancellation technique. So
Right.
they separate the noise that are coming from far beyond. So can't we use that here? Means it also will reduce the noise, and we will get a better picture of what is coming there. So using the same technique, we can do so, I think.
Right. Um, right. So the way I think like the phone is able to cancel any noise which is currently happening is because like it's cut like there's a I think particular range in which it identifies that I'm speaking and rest all is being classified as noise. So there might be some significant noise which you should hear, but you're not able to hear because it's not of certain pitch or certain
No, no.
frequency.
I have seen some videos regarding the noise cancellation technique. It's means if you are talking to someone and any baby cries or something else happens,
Mhm.
it also judges that also and cut it down. So
Right.
there won't be anything like that.
Right. So for that also, like the way I see it is, and could be wrong. Anyone of you can correct me here. But even for this, like we here when I'm actively canceling noise, it's because I want no noise in the real time. But when you're recording sound underwater, that's not really the case, right? You do not really require the noise to be cancelled, and it requires significant. Like even this would actually use up some energy. And these underwater hydrophones which are deployed are actually costly deployments. So at once they are like once deployed they're left for a very long time. So in itself the deployment is pretty costly, but in case you also want to supply energy and actively cancel data, it'll result in significant cost, plus there's no real need to actively cancel noise. You can take all the data later on and then process the noise out yourself. So I think it's the time, like effort that we'll have, and it'll just be costlier to do it underwater, I believe.
There is no
You are
need
telling you
for
will do it after taking the data.
Shraddha, there is no
Just
need for doing that noise cancellation in real time, is there? You can
okay,
always
sir.
pass the filter and take the noise out at a later point, right?
Okay, sir.
What is the advantage we get by doing it in real time?
Sir, we will get much pre-processed data within our data set. So that's what.
You can just process it with a simple click of a filter. You just cut off all the frequencies which are not relevant for you and off they go. I mean, for a active noise cancellation is required when you are looking at a real-time system, isn't it?
Yes, sir.
Particularly, it won't be so relevant for a underwater hydrophone. In fact, you might want to be interested, you might be actually be interested in the higher frequency things too, right? Because there may be noise plus something relevant may also creep into those regions. You don't know the data right now. Because if this were a supervised problem, you would precisely know these are the fish I want to classify. So, and this is the frequency range that I'm looking. But here the problem is inverse, right? I just give a raw data set and I want to figure out what all are there in it. So how do we know that the range of frequencies which we want to cancel, there may not be something interesting there? No way of knowing ahead of time, isn't it?
Yes, sir.
Right? So for that reason, probably it may not make sense is what my thought process is. Okay.
I have one more thing. On canceling headphones, it cancels out all the noises, right? Whatever is the ambient noise, it cancels everything and it just plays whatever is coming from the system.
Aditya, we are unable to hear you very clearly.
Am I audible now?
No. speaking on a railway.
Am I audible?
Yes, much better.
Sir, so noise cancelling headphones, it actually cancels all the noises from ambient. No, sir, it doesn't just cancel any particular frequency or something. It cancels out everything, and it just amplifies whatever is coming from the system. So
How are you detecting what is ambient?
it has microphones, right, sir?
Correct. So it is detecting that ambient noise ahead of time or during the time, right?
Yes, sir. So how we cannot apply that even real time or even after that, because we need all the frequencies, right?
Correct. We definitely need all the frequencies in our case, but I'm just curious, even when you are doing a noise cancellation, you should not be cutting off the person's voice itself as noise, right?
Yeah, sir, I don't think we can do it when the person is speaking, sir. The noise cancelling works only when you're listening.
No, not quite. I think what is happening there is they have their microphones are collecting the noise, and they generate a profile for the noise frequencies, and that frequency range you are cancelling out
Oh,
when you are actually going into your audio call.
okay. So because
That's what I would presume.
so no, I thought they worked like they cancel out the noise by producing anti, like, what to say, uh, other, sir, like,
Like negative sound, and
Like a
they.
feedback system. I'm not sure about the technology. Maybe some of you can read up on it and update.
Even like I have also read somewhere that they produce a negative sound, so they
yes, sir.
superimpose.
So they are actually pumping noise into your
Yeah,
headphone, which
yeah,
is opposite of what is there in the amp.
yes. Yeah, they are
No,
super.
actually, that is something different. That is like you have different modes in some sort of earphones and all, which allow environment voice to come, noise to come in. Those
Okay.
earphones use counter sounds to cancel noise. But in normal systems like your phone or your laptop, they doesn't use extra microphones to cancel those sounds. They just have a preset frequency range which they identify it as non-noise. I don't know what is the correct word for it, and they allow those sounds only.
Okay. All right. Now, can somebody tell me for sure that you actually have systems where they are actually pumping the negative of the noise which you are hearing from the ambient?
Yeah, so like if you have gaming earphones, it
This
happens sometimes.
technology is used by Apple's in their headset.
It's
That
used by
Like
sir,
AirPods.
Apple,
Apple. Okay.
Yeah.
they use it.
Okay, I have heard about the idea that there is a microphone on the back which is looking for the ambient noise on headphones. Okay, for example, like a Bose noise cancelling headphones and other things. But I'm not quite sure that they're actually pumping noise.
No, sir, they create the phase such that they cancel out the amplitudes.
Okay, all right. So they are actually able to do that, active noise control. Okay, so there is something in that direction. Okay, all right. That's news to me. I always used to think that they will collect the noise and be observing the frequency range in which the noise is there and then apply the cutoff frequency into your existing. They'll basically filter your total sound through that in order to reduce the noise effect.
Yeah, that is traditional noise cancellation methods.
Correct. Correct.
I feel that this one would be faster than like just add the negative to.
But
Yeah, but
active noise cancellation might sometimes lead to delays, slight
it may
delays.
lead to delays.
Yeah, because they need to superimpose and process the sound before injecting it into someone who is listening. So there, sometimes people report that there is a small lag in all these earphones and headphones.
Oh, is it? So it's not.
Perfect, but yeah, it's
So it's
very
not
nearly
real
there.
time. There is a lag, you mean to say?
It's not a huge lag, but like some milliseconds and all.
Okay. Interesting. All right. Somebody else also had a question. Manoranjan?
Yes, sir. So I had a small suggestion here. So there are something called as MFCC coefficients. So what it will do, it's basically used in voice recognition systems. So the way you see, like when you speak something, you can see that automatically translates to text, right? So those things kind of use MFCC coefficients. So you can choose the number of coefficients, and what it will do is it will try to approximate the wave. So the lower order coefficients tries to get an overall idea of the waveform, and similarly as you increase, it will try to add in more frequency ranges. Or there are a lot of properties to MFCC coefficients, and also there are similar types like MFCC. Maybe you can try to have a look at it as well. I'm not sure how whether it will work or not in your case, but maybe worth a try.
I think definitely worth it, Mansi.
Yes, sir.
It's definitely used very often.
So it basically indirectly, I mean, it indirectly computes the FFT and I think discrete cosine transform or something. So it may be useful for in your case. Yeah.
Sure.
Definitely
I'll
worth
read
the
up on that.
Yeah, definitely worth the read to look up what they are, how they are computed, how will they be useful or not. Okay.
So MFCC, I think another one may be LPCC or something. So maybe you can take a look at it.
Okay.
Sure.
Good. Excellent position. Any other thoughts, comments? Okay, all right. If there are no other thoughts and comments, we will try to look. One thing which I did want to ask Mansi, in this particular case, when we are, let's say, we're only looking at the spectrogram and trying to do the classification, what will be your hyperparameters which we might require to tune in order to make the model work out better? What are the hyperparameters that you can think of which may be relevant in this particular scenario?
Right, sir. So I think one, it should depend upon the model that I'm trying to use, and finally which features you're extracting. So besides frequency, I think, like I said, I would want to see the time duration. So that would be one of the other parameters I'd want to look at, but not really sure at this stage what other hyperparameters should I look at.
Yeah, I think one of the main aspects would be, for example, if I were to think about it, I would say number of clusters. How many
Yes, sir.
clusters you want to classify the data into? That would be one major hyperparameter that you want to choose. Right? Also, the other thing which you will probably want to choose is how quantized your frequency domain data is. Which means, are you collecting the frequency information every 1 hertz difference, or zero point 0.1 hertz, or 0.01 hertz? How finely quantized is your feature vector? Because the more quantization you add, the bigger your feature vector is becoming, the more computationally expensive it will be to perform the classification. Right? So there has to be some balance between the amount of computation required versus the number of quantization needed. There should be some basic boundary on how much maximum quantization can I take in the frequency domain, such that I'm still able to classify the species of interest for me. Okay, and that again ties back to the question of Aditya. If we don't know what we are looking for, this may be a problem, right? So I suggest that these might be some of the issues for which you might have to look at some of the literature and see whether there is something going on in that direction. Okay, and definitely we'll also try to take a look at the other features, the melt frequency coefficients, MFCCs, and the other ones, and understand how are they fundamentally different from an FFT, and what extra information they can add. I think these are the directions definitely one should be looking at. Right? All
Yes,
right.
sir.
Now, when you're trying to access this data, I know that there's like about 140 terabytes of data on AWS, so it doesn't make sense to download all of the data and be able to work with it. So what do the tutorials tell you? How to access the data and how to go about it?
Right, sir. So in the tutorials, they have given us ways to access data from particular month and particular days, and you can just change the names of those directories and access data for different months. And within those also, you can select which day you want to look at and which hour you want to look at.
Yeah, I
So
guess that is
that
by
way,
the name they have classified, right? They have given classification by the year, name, date, and so on and so forth.
yes,
But
sir.
so when you're processing on, let us say, 1 day's file, say 30-minute record, okay. When you do you pull down the record and then you work on it, or is there a way for you to actually perform the computation on the AWS servers itself? I presume that right now you're pulling down the data and then you're working on it.
Right. So in the tutorials, we are just like analyzing one piece of data where they know that there definitely is a fish species, so that
Correct.
we can classify it. But I think in one of the data sets, I'm actually able to download the data and I tried making spectrograms out of these data. So I have to still work on the pre-processing part, but I am able to download it if I want to download them individually as 1 hour clips.
Correct. So I think one other parameter which might be of interest is what should be the window of the data that you should look at. So how many seconds of window should you look at if you want to actually get declassification right? Right. If it
Yes,
is a
sir.
whale call which is lasting for a few hundreds of seconds, and I give you only 5 seconds of that data, it may not make much sense to get something out of it. Right.
Yes, sir.
So the window size may also be a parameter which might be relevant when you are constructing your spectrograms, right?
Yes, sir.
So that might be something to look at. Okay, sounds good. Any other queries or thoughts or comments before we wrap up? No other comments? All right, in that case, let me stop recording.